Hi everyone, welcome to this series of videos on quantum mechanics. This series is going to be about the tenets of quantum mechanics, and the idea is to explain quantum mechanics to who doesn't know this theory. A minimal amount of knowledge of mathematics and possibly of classical mechanics is required, but if you are not an expert in these things, do not worry. Try to bear with me and follow. The way I'm trying to explain quantum mechanics in this series is very simple and at a very high level, in the hope that it can be helpful and useful to anyone that would like to have at least a high level idea of what this theory is. So in this very first video, we are going to talk about classical mechanics, and we will go from classical to quantum mechanics. It is important to know a little bit of classical mechanics because this can help a lot if you want to understand quantum mechanics. So this video, but also the other videos in this series, are based essentially on these three books that I am presenting here. They all of them talk about quantum mechanics, of course. The first one is Quantum Mechanics, published by Landau and Lifshitz a while ago. This is a very important book. It's on the non-relativistic theory of quantum mechanics. Essentially, most of the text that you are going to see in these videos is taken from this book. But we will also refer from time to time to two other excellent books on quantum mechanics. The first one being Quantum Mechanics by Albert Messier, and the other one being Quantum Theory by David Bohm. The three books together complement each other because they present the same mechanics, quantum mechanics, but from very different perspectives that complement each other. So it's interesting to have a look at these three books, and I would definitely encourage you to do so if you haven't done that yet. Some preliminary note is also important, and in particular about the formulations of quantum mechanics and the interpretation of quantum mechanics. Nowadays, many formulations exist. For example, we have the very first one that was introduced by Heisenberg, but then we also have the Schrödinger one, and we have also formulations that have been introduced by Feynman, Wigner, and so many others that you have probably not even heard of. All these formulations are equivalent in a way, in the sense that predictions are all the same. So from the perspective of predictions of a system, any formulation you are going to use is equivalent, so we don't have any preference from this perspective. And in these videos you will see that we use mainly the Schrödinger formulation, but from time to time we are also going to use other formulations because they provide a better view or a simpler view over a system at hand, just because they use a different mathematical framework. Some note also on the interpretations of quantum mechanics. Of course, nowadays many interpretations exist. For example, we have the Copenhagen one, we have the many worlds one, we have the pilot wave one, but we have so many others. We will not prefer any particular interpretation here. So we will actually try to use these interpretations depending on the context we have at hand, in the hope that a different interpretation can provide a better view over the system at hand. So we can now start by answering the question, what is specifically quantum mechanics? And quantum mechanics is not extremely difficult to explain from this perspective. It is the theory that describes and explains very small objects such as atoms and molecules. Quantum mechanics actually appeared as a necessity because about a century ago, physicists realized that classical mechanics was very, very useful to describe macroscopic objects, but was not reliable in describing or predicting the behavior of microscopic objects such as atoms and molecules. So quantum mechanics is essentially the theory explaining the functioning of atoms and molecules. And we can now go to the concept of space and time. These are very, very simple concepts, and one might ask himself or herself why we should introduce the concept of space and time. It is actually very important because this is essentially the framework under which we are going to build the whole theory. So it is important to specify what kind of space and what kind of time it is utilized in classical mechanics, but also in quantum mechanics. And first of all, we have a few assumptions on what space is and what are its characteristics. So first of all, space is a three-dimensional, which means that essentially you need three variables or three numbers to describe the position of an object. And space is also considered in this context Euclidean, which means that the space we are going to use is exactly the same space that is used in classical geometry. Space is also considered to be homogeneous, which means that we expect that the laws of physics are exactly the same everywhere at any point in space. So if you have a system that is localized around one point, this system, if it is translated towards another point without any modification, then this system must behave exactly in the same way. Space is also isotropic, which means that the rotation of, let's say, a physical system without any modification is not going to affect the behavior of that system, or in other words, the laws of physics do not depend on the direction in space. The same we have for the concept of time. Time will be considered as one-dimensional, which means that we need only one number or only one variable to describe time. And time is also considered to be homogeneous, which in short means that we do not expect the laws of physics to change in time. So these are postulates that are very important and specify what space and time is. These postulates are important in classical mechanics, but they are going to be very, very important in quantum mechanics as well. We can now go through the concept of particle, which is another concept that is very, very important in classical mechanics. So what is essentially a particle? A particle can be considered a body whose dimensions can be neglected if compared to the characteristic length of its motion. So to make a very specific example, a very concrete example, one might think of a planet like planet Earth, for example. If our goal is to study the trajectory of Earth around the Sun, then the trajectory is so big that the dimensions of the Earth can be neglected, which means that essentially in this particular context we can consider planet Earth as a particle. But if our goal is to study, for example, the effects of the rotation around its axis, then the Earth might not be considered as a particle, because now the characteristic lengths of the dynamics and the motions of the Earth are comparable to the dimensions of the Earth itself. Also, another concept that is very important in classical mechanics is the concept of Cartesian coordinates, and Cartesian coordinates are going to be important in quantum mechanics as well. By Cartesian coordinates, essentially, we mean the following. If we have a particle, the position of this particle in space can be defined by its radius vector r, which components are essentially the Cartesian coordinates x, y, z. So, in a sense, you can consider these as free variables that describe the position of a particle in space. And the way it is done is with respect to frameworks that you can see, for example, on the bottom of this page. The left-hand side framework is for a two-dimensional space, so you need only two Cartesian coordinates, x and y, to specify a position, while the right-hand side framework that you see here is a three-dimensional space, which means that your Cartesian coordinates will be specified by three numbers x, y, and z. At the same time, now that we have the concept of a radius vector, we can define the derivative of a vector, which is, for example, this derivative v here, that is equal to the total derivative of r with respect to t. And v in this case is called the velocity of the particle. And in the very same way, one can define also the acceleration of a particle by taking the second derivative of r with respect to the variable, the time variable. So sometimes also in physics we use a different notation for the derivative, so we could switch from dr over dt, but also we could write, for example, the velocity as equal to r with a dot on top of it. The dot means essentially first derivative with respect to time. If you want to, for example, in this very same notation, you want to express the acceleration, this would be r with two dots on top of it. And in the same way now we can also introduce the generalized coordinates, which is another very important concept that has been brought by classical mechanics. So imagine that you have a system that is made of n particles in space. In this particular case, this means that we are in the presence of n radius vectors, and every of these radius vector is specified by three coordinates, the Cartesian coordinates or the components of the radius vectors. So in this particular case, if we have n particles in space, one can say that we have 3 times n coordinates. And still in this case, we could say that 3 times n is the degree of freedom. What is the degree of freedom? Essentially, this is a number that must be specified, or let's say it's the number of independent quantities that must be specified in order to define uniquely the position of a system. So in this particular case, if you have n independent particles, you will have 3 times n being the degrees of freedom of the system. But of course, Cartesian coordinates are not the only way to represent a system, and actually you could think of many different ways to represent the position of that system. So in particular, any s quantities, q1, q2, so on, and qs, which completely define the position of the system, are essentially valid coordinates, which are not called Cartesian coordinates anymore, but they are called the generalized coordinates. And S in this particular case is the degree of freedom. In the very same way that we have just seen before, you can denote the derivative of the generalized coordinates with a dot on top of it, and in this particular case you will call this a generalized velocity. So to make a concrete example here, you might think of this point here that I am showing here with the mouse, you could think of this point as essentially a particle that is attached to a rod, and the rod is attached to the center of this circle here. So you can imagine this particle moving in this circle here forever. So one could recur to Cartesian coordinates and use two numbers, since this is a two-dimensional space, and practically describe the position of this point through two numbers. But that would be actually more than what we need. As a matter of fact, since you know that the particle will always be on the circle, you could actually use this variable A here, which represents the angle that is being practically represented by the particle and this axis here. And the angle would be only one variable that is enough to provide the position of the whole system. So in this particular case, this would mean that the degree of freedom is 1, because we need only one variable to describe the system uniquely. And at the same time, the generalized coordinate here would have nothing to do with Cartesian coordinates, because it would be an angle. So now we are ready to introduce the concept of equations of motion, which is of paramount importance, of course, in physics, classical physics for sure, but also in quantum mechanics as well. We know from experience in physics that if all the coordinates and velocities of a system are specified simultaneously, it is then possible in principle to calculate the subsequent motion of the system itself. Mathematically, this means that if we provide all coordinates q and all velocity q dot, essentially at some instant, of course, essentially then the acceleration q dot dot at that instant are uniquely defined. So this means in practice that we are capable of providing relations between accelerations, velocities, and coordinates. And these relations are what we call the equations of motion. Of course, since we are dealing with accelerations, these equations of motion are second-order differential equations for the function q, which depends on the variable t. And in a more general way, one could say that the whole system is at the end specified by a function that, for example, the function L that you see on the bottom here, that is going to depend on all positions, so q1, q2, and qs, and all velocities, q dot 1, q dot 2, and so on, q dot s, plus the time variable t. So far we have explained what the equations of motions are, but how do we calculate these equations of motions in practice? And for that, I mean, classical mechanics has brought us a very important principle that is called the principle of least action. And what this principle says is quite simple. If you suppose that a system occupies at instant t1 and t2 positions which are specified by coordinates q1 and q2, then the system is going to move in a way such that the integral that you see here, this integral here, the integral between t1, t2 of L in dt, this integral will take the least possible value. The function L in this particular context is called the Lagrangian function of the system, and the integral that you see here is called the total action of the system. And by applying this principle of least action, what one can show is that if we are in the presence of one particle only, then we can say that essentially the variable the function L will follow this equation here, while if we are in the presence of, let's say, n particles which are represented by s variables or s these, let's say, generalized coordinates, then these equations here will hold for the Lagrangian of the system. And this is a very important principle because it brings us eventually to find concretely the equations of motion of a system. So what can we say about the Lagrangian of a system? Because so far we have been describing this function but without providing any explicit expression. In this particular case, we can find a mathematical expression of the Lagrangian by using the Galileo relativity principle, which says that the equations of motion have the same mathematical shape in any inertial reference frame. And I will not go through all the details of this principle because this would completely bring us in a different direction. Plus, one can find more details in the books that I have just suggested. So, for example, the Lagrangian of a free particle can be computed, and in this particular case it would look like what you see here, but in the same way one could deal with, for example, Lagrangian corresponding to systems of particles or independent particles, but also one could find in the same way the expression for the Lagrangian of a system of interacting particles. A very interesting thing to see here is that the Newton equations that are very well known in physics are actually a very particular case of the equations of motion that we have just introduced here. In fact, if you take, for example, a system of n interacting particles, the Lagrangian will look like the following one that you see here. And this is coming from the Galileo principle of relativity. If you substitute L in this equation here, and if you do the calculation, you will end up having this equation here. And this equation here is still an equation of motion, just that the particular form of this equation that you see here is called the Newton's equation. And this practically is the basis of the mechanics of system of interacting particles. Sometimes this term here is called the force, and it's practically denoted by the letter F. In the same way, it is possible to show that Newton's equations are not the only possible equations of motion. For example, other formulations exist in classical mechanics which equivalently describe a classical system. Among all these formulations, the equations of Hamilton are of paramount importance because this is essentially a formulation that can show the connection between classical mechanics and quantum mechanics. And in the Hamilton equations, essentially now we are in the presence of different concepts. In particular, one has to compute what is called the Hamiltonian function, which is defined as the one that you see here. So if you have the Lagrangian of a system, you are capable of finding the Hamiltonian of the system, and then by using these two equations here, or let's say the set of these two sets of equations, one is capable to recover the equations of motion for every particle that belongs to the system. So since this Hamiltonian formalism is more important in this particular perspective because we are going towards quantum mechanics, I extracted one very simple exercise from Landau that I suggest anyone interested to try. It's quite simple, but it's an important one. And what it says, the problem says that find the Hamiltonian for a single particle in Cartesian, cylindrical, and spherical coordinates. So I recommend to try this, and I am leaving the solution here for whoever is interested in trying to calculate these Hamiltonians. And this concludes this first video. I thank you very much for your attention.